Hello. I wanted to go through exercise 17 exercise 6H, question 17. It's here. You have to derive this distance equation, and then you have to derive this secondary distance formula, which is quite useful. So let's explain it. They've got a diagram here to help. We've got Q, I'll start with Q as a point. Now this is a generalized point that could be anywhere on the plane. So this will just be some x, y, z. You've got your plane equation. Normally we would see ax plus by plus cz equals d, equals the constant. They've just moved the constant over to the left. That will become clear why they did that when you get down to this formula, because you need the d in that formula. This point here, this is a point here at the end of some line. That is a specific point, so it's got some values to it, like x is some number, right? So that's like a fixed point that you would usually know what the numbers were, as opposed to q, which is some generalized point on the plane. So I've drawn a picture of this here. All right, and you can see I've put in point P with the ones, so that's meaning it's some specific values, as opposed to the x, which is any old x, y, z. We've also got n, which is the foot of the normal here. D is not a vector. D stands, as you would think it would. It stands for a distance. You could say it was the magnitude of vector np, right? But it's not a vector itself. Now, to do the question, I'm looking at where I've got to go, which I've written here. So they're telling me show this formula. Okay, so I look at the formula and I think, it looks a lot like something I'm pretty familiar with. This when I'm finding angles between two vectors. And that normally would look like this. All right, so it's the dot product divided by the magnitudes of each vector just multiplied together. We put it inside of a modulus so that if this number here comes out negative, we make it positive, and then we get the acute angle between the two vectors, right? So you've got vector v, vector w, and you're normally using this to find an angle in between them in this type of setup here, right? We've got something close to that in our diagram. I'm going to draw a line in. I can see that they want vector QP, so I'm going to draw it in from Q to P there. Just label it QP. All right. They want me to use the normal. That's fine. All right. That's pretty obvious. So the normal, right, go back to black. I can get from the plane equation, because the Cartesian equation of a plane is derived from the normal vector to the plane, because we know that the dot product of this normal with any vector on the plane, like here's one, qn, so the dot product of qn with n, or this normal vector, would equal 0. So that's how we get our plane equation. And once we've got it, we can see the normal really easily. It's just the coefficients a, b, c, right? So that's fine. I can use the normal. The normal could be anywhere on the plane, could be there. But given the similarity with this angle between two vectors formula and this picture that I've got in my head of what that looks like, it would make sense, I'm just going to erase this one, to draw that over here, right? So if I put my normal in there, and I would be finding an angle here, right? Now I guess you could draw it there as well, but I'll just do it this way, that's fine. Now that I've put in QP, I'm also seeing a right angled triangle. I'm seeing cos theta in a formula that looks really similar to the one they want me to derive. I'm seeing a right angled triangle. I'm thinking, yeah, cos belongs with right angled triangles, so I might just, while I'm thinking about it, what else do I know about cos theta? It's an adjacent divided by a hypotenuse, right? And that's kind of fitting with this right angled triangle picture. Although our triangle is maybe, you know, do I think of a triangle up here? I could. What I might do though is put theta into the triangle. This is just 90 degrees. That would be 90 minus theta, or using alternate angles, we could put it in here, right? Because vector NP is also perpendicular. That's in the diagram. So, you know, I've got, in my picture, I've got this sort of situation here. I've got a theta there and a theta there with these parallel lines, right? So they must be the same. Those are alternate angles. Which would mean what? It means if my theta's there, this is good because D becomes an adjacent, right? And the hypotenuse, yep, that's good because that's in my formula that I'm trying to show. That would be the magnitude of the vector QP, like that. I guess that then, therefore, we could say that cos theta, so if cos theta times the hypotenuse, I'll just write h equals an adjacent. For us, cos theta times the magnitude, sorry, I should have put in magnitude, of vector QP gives us our distance. All right. Okay, let's go back to this. I'm going to start with the cos theta formula, which looks so similar to what they want me to show. And if I was doing that, I'd be writing QP dot n, you can see it on my diagram, divided by magnitude QP, magnitude n, those two numbers times together. I look back at what I'm supposed to show and I think, oh, the right hand side, I can make it exactly the same if I bring over the magnitude of QP. So if we multiply both sides by that, then we'll be left on the right hand side with what we wanted, right? So that small little modification. And because I've done some thinking over here, I can see, cos theta times magnitude QP is just the distance, right? So therefore this equals distance, right? You'd want to have, off to the side, you'd want to be explaining some of this. I've probably written a bit too much explanation, but you could put in brackets off to the right how you've figured out that D is the same as cos theta times magnitude QP. And if you've drawn yourself a diagram, it makes sense. All right, I'll stop the video there and then I'll do part B.